Welcome back to Mechanical Engineering Made Simple.
It's really fantastic to be back.
Today we are going to dive into a story about a device that I think um, every single engineer or tinkerer has underestimated at least once in their life
Oh, definitely.
because it looks deceptively simple,
Yeah.
right? It's essentially just a spool of copper wire and a chunk of steel.
You are talking about the solenoid actuator.
I am, and honestly, it's a classic trap. You look at the diagram, and it's just a coil and a plunger. You think, how hard can this be? I run current, the magnet turns on, the thing clicks.
Right.
But then you actually build one, or you try to troubleshoot one in a piece of industrial machinery,
Yeah.
and you realize that getting that satisfying snap involves some seriously nuanced physics.
It really does. I mean, on paper, it is the simplest machine in existence, but the gap between making a magnet and making a useful actuator that actually does work is huge.
Yeah.
That gap is filled with concepts like inductance, reluctance, and the principle of virtual work.
And to navigate that gap for this deep dive, we're going to follow the very real struggles of a protagonist we'll call Alex.
Okay.
Now, Alex is a mechanical engineer working on a pretty high-stakes project. He's designing a safety locking latch for a pressurized industrial door.
Oh, wow. Okay, so this isn't just a toaster lever. If this latch fails, the door could blow open, or the safety interlocks could fail. The stakes are real.
Exactly. The requirements are super clear. When the control system sends a signal, a steel bolt, which is our plunger, needs to shoot forward, compress a heavy spring, and lock that door solid.
Which is a very standard linear actuator application.
Right. So Alex does what any of us might do. He grabs a plastic spool, winds a few hundred turns of magnet wire around it, sticks a steel bolt about halfway into the hole, and hooks it up to his 24-volt power supply.
Sounds reasonable so far.
He's ready for the big moment. He flips the switch, expecting a loud industrial clunk.
But I can already see where this is going.
Yeah, instead of a clunk, he gets a twitch.
A twitch.
The bolt kind of lazily slides forward maybe a quarter of an inch, vibrates a little bit, and then just stops. It doesn't even come close to compressing the locking spring.
It's weak.
It's weak. It's sad.
Yeah.
And Alex is standing there scratching his head thinking, I have current flowing. I have a magnet. Why do I have zero force?
That is the classic twitch of failure, and I bet I know what his first instinct is to fix it.
Oh, absolutely. He looks at the power supply dial and thinks, I just need more juice.
Right.
He's about to crank the voltage from 24 up to 48.
Which is the engineering equivalent of just yelling louder at someone who doesn't speak your language.
It really is.
Yeah.
And before Alex melts his coil into a puddle of copper and plastic, let's freeze time.
Yeah.
We need to help him understand why his latch is failing.
Yes.
And to do that, we have to look at how we actually calculate the force on that plunger. Because it turns out there's a hard way to do it and a smart way.
And unfortunately, most of us learn the hard way in physics class, which is exactly why Alex is confused right now. He's probably thinking about the Lorentz force.
The Lorentz force.
Yeah.
That's one we all memorize, right? F equals Q, E plus QV cross B.
Right. It tells you the force on a single charged particle moving through a magnetic field. It is strictly, fundamentally true. Every single electron spiraling through Alex's wire is experiencing this force.
So Alex is thinking, okay, I just need to sum up all those forces.
But think about what that actually entails. You have a spiral coil, so the current direction is constantly changing in 3 dimensions.
Yeah.
You have a magnetic field that curves and changes intensity depending on where you are in the coil. To calculate the net force on the plunger using Lorentz, you would need to do a vector cross-product calculation for every differential element of the wire and the core.
Which is a vector calculus nightmare.
It is entirely computationally exhausting. It's like trying to predict the flow of a river by tracking every single water molecule individually.
Right.
You might get the right answer eventually, but it gives you zero intuition about how to fix the physical design.
So we abandon the hard way. We need the smart way.
Right.
And the sources call this the energy method.
Or the principle of virtual work. This is the exact shift Alex needs to make. Instead of asking what is the force on this electron, you ask how does the energy in the system change if I move the plunger?
Okay, let's unpack this. We're moving from vectors to energy. How does that help us find the force?
Well, think about a ball sitting at the top of a hill. Why does gravity pull it down?
Because the ball wants to lower its potential energy. It wants to go from a high energy state to a low energy state.
Precisely. Electromechanical systems have a very similar drive. The magnetic field stores energy. And the system will generate a force to rearrange itself into a state where it can store that energy most efficiently.
Okay.
In the case of a solenoid, the system wants to maximize its inductance.
Maximize inductance. It sounds like a textbook catchphrase, but what does it actually mean physically? What is this system trying to do?
Think of the magnetic field lines like a stream of water. They really, really want to flow through iron. Iron is like a wide open pipe for magnetic flux.
Right.
But air is like a clogged pipe. It's very hard for the field to travel through air.
Okay, so in Alex's broken latch, the plunger's sitting halfway out. There's a big air gap inside the coil.
Exactly. The magnetic field is trying to complete its loop, but it has to jump across this massive gap of air. It's strained, it's inefficient. The inductance is low because the path is so difficult.
And the system knows that if the plunger were to move inward, that air gap would disappear.
Okay, yes. The system senses that moving the steel plunger into the gap will make the path easier. It will increase the inductance. So the force you feel, that physical pull on the plunger, is actually the system trying to grab the steel and stuff it into the air gap to make the magnetic flow easier.
That makes so much more sense than calculating electron vectors.
Yeah.
The force is just the system trying to close the gap.
Correct. And we can actually quantify this. The sources give us a specific equation that really illuminates Alex's problem.
Let's hear it.
The force is equal to 1/2 times the current squared, multiplied by, and this is the key term here, the change in inductance with respect to position.
Okay, let's visualize that equation. Force equals 1/2 I squared times dl dx.
Exactly. dl dx. That is the derivative. It represents the slope of the inductance. It basically asks the question, if I move the plunger 1 millimeter, how much does the inductance improve?
So it's a bang for your buck calculation.
That's exactly what it is. If moving the plunger gives a huge increase in inductance, a huge improvement in the magnetic path, then dl dx is big, and the force is huge.
Yeah.
But if moving the plunger barely changes anything,
Then the force is tiny. And I think we just diagnosed Alex's problem.
we did. Alex has his plunger starting way out in the air. The air gap is huge. When the plunger moves a tiny bit from that position, the magnetic path doesn't get that much better. It's still mostly air.
So dl dx is small.
It's very small.
Yeah.
The system effectively shrugs and says, well, moving the plunger doesn't really help me much right now, so I'm not going to pull very hard.
But as the plunger gets closer,
As it gets closer, it starts to bridge the gap. Suddenly, every millimeter of movement drastically improves the magnetic path. The inductance skyrockets. So dl dx becomes massive, and the force spikes.
this is a huge realization for anyone designing these. A solenoid isn't like a hydraulic piston that pushes with constant force. It's highly nonlinear. It's weak at the start and incredibly strong at the end.
Which is terrible for Alex because he needs to compress a heavy spring right from the beginning of the stroke. He is trying to start his movement in the dead zone.
So cranking the voltage isn't the answer. He needs to fix the geometry. And this leads us to another concept from the notes that helps visualize the fix, which is the magnetic circuit.
Yes, this is the bread and butter of magnetic design. Electrical engineers love circuits, so we just map magnetism onto circuit rules. It makes things so much easier to see.
So let's run the comparison. In an electric circuit, you have voltage pushing current against resistance.
Right. And in a magnetic circuit, you have magnetomotive force, which is your number of turns times your current, or N times I pushing magnetic flux against reluctance.
Reluctance. I love that word. It just sounds like the material is stubbornly refusing to cooperate.
That is exactly what it is doing. Reluctance is a measure of how much a material resists magnetic flux. Iron has very low reluctance. Air has massive, huge reluctance.
So looking at Alex's latch through this lens, he has a circuit. The coil provides the push, but his circuit has a giant resistor in the middle of it, which is the air gap.
He's trying to drive current through a brick wall, the force we talked about earlier. Another way to define it is that the system is trying to minimize reluctance. It wants to delete that air gap resistor and replace it with a short circuit of steel.
So knowing all this, the energy method, inductance, reluctance, how does Alex actually fix the latch? He's sitting there with this twitching bolt. What does he do?
He needs a 3-step plan. First, geometry. He has to redesign the mechanism so the plunger starts deeper inside the coil. He needs to eliminate that initial dead zone so that dl/dx is high right from the very start.
Don't ask the solenoid to pull from across the room. Got it.
Second is the return path. This is a super common rookie mistake. The flux goes through the center of the coil, but how does it get back to the other end?
Usually just through the air around the outside of the coil, right?
Right, and that is a huge source of reluctance. The air outside the coil is just as bad as the air inside. Alex needs to wrap the coil in a steel shell or a C-bracket. He needs to build a magnetic highway for the flux to loop back.
So he's encasing the coil in iron to keep the reluctance low for the whole entire loop.
Exactly. And third, materials. He needs to make sure his plunger is made of a high permeability steel. If he's using standard stainless steel, for example, some grades of that are non-magnetic. That would be like using plastic. He needs a material that loves magnetic flux.
Okay, so let's fast forward. Alex takes this advice. He adds a steel bracket around the coil. He adjusts the mounting so the plunger starts closer to the center. He flips the switch again.
And this time, snap.
It hits hard. It compresses the spring. The door locks.
He didn't just add power. He removed the resistance, or rather the reluctance that was choking the system. He worked with the energy field instead of fighting it.
Now that's a massive win for Alex. But I want to complicate his life a little bit. Let's say, theoretically, Alex gets bored with safety latches. He sees this solenoid and thinks, you know, if I don't put a stopper on this, I could shoot this bolt right across the room.
The coil gun pivot. Every engineer tries this eventually. Can I make a projectile launcher?
But the notes mention a specific trap here. It's a dynamic problem called the suckback effect.
This is a great cautionary tale about the energy method. Remember the golden rule. The system wants to maximize inductance.
Right, and inductance is maximized when the iron core is perfectly centered inside the coil.
Correct. So as the bolt is flying towards the center, the force is pulling it forward. It's accelerating. Life is good. But what happens the instant the bolt passes that center point?
Well, now it's leaving the region of maximum inductance.
Exactly. It's moving into a state of lower inductance. And since the system hates that, dLEDX flips its sign, it becomes negative. The force reverses direction instantly.
So the coil stops pulling it forward and starts yanking it backward.
It tries to suck it back into the center. If Alex just leaves the power on, the bolt will shoot forward, get yanked back, oscillate a few times, and just settle in the middle. It won't launch at all. It'll just get trapped.
So to make a coil gun, you really had to be faster than the physics.
You have to cut the current. You need to kill the magnetic field at the exact microsecond the projectile reaches the center. You pull it in, and then bam, turn off the magnet so it can coast out on its own momentum.
But that timing seems impossible to just guess. The bolt is moving fast. How do you know when it's there?
This brings us to another fascinating concept from the source material, which is back EMF.
Back EMF, we usually talk about that with motors.
Well, solenoid is just a linear motor. As that steel plunger races through the magnetic field, it disrupts the flux lines. Faraday's law of induction kicks in. The physical movement itself induces a voltage in the wire that opposes the current you're putting in.
So the faster the bolt moves, the more pushback voltage you get.
Exactly. And if Alex is clever, he can use this. If he hooks up an oscilloscope like they do in the lab modules, he can watch the voltage across the coil. He'll see a spike or a dip that perfectly corresponds to the speed of the plunger.
The coil is basically acting as its own speedometer.
It is. He can use that signal to trigger the shutoff. He's using the interaction between the mechanics and the electronics to time the shot perfectly.
That is incredibly cool. It's using the problem, the back EMF, as the actual solution.
That is the essence of good mechatronics design right there.
Okay, so we fixed the latch and we built a theoretical coil gun. I want to pivot now to the post-mortem. Let's look at the frequently asked questions. These are the things that Alex and you listening might run into after you build the thing.
The why is it doing that phase.
Exactly. So scenario 1, Alex's latch is working. It snaps shut. But he leaves it locked for an hour. He comes back, touches the coil, and burns his finger. It's incredibly hot.
This is the most common complaint with solenoids. And it goes straight back to energy conservation.
We're putting electrical energy in.
Right. And we want mechanical work out, which is force times distance. But think about it. Once the latch is closed, is it moving?
No, distance is 0.
If distance is 0, mechanical work is 0. So you are pumping 24 volts and maybe 2 amps into this coil. That's 48 watts of power. Where is it going?
It's not moving the bolt, so it has to be heat.
100% of it becomes heat.
No.
It's just I squared R losses. You are essentially turning your latch into a very expensive, very inefficient heater. Solenoids are notoriously bad at holding a position.
So did Alex design it wrong?
Not necessarily, but he needs a control strategy. Real industrial controllers often use a hit and hold circuit. They hit it with high current to get that big dLdx snap, and then once it's closed, they drop the voltage down to just a trickle. Just enough current to keep it there without melting the insulation.
That makes a lot of sense.
Yeah.
Okay, scenario 2. Alex thinks, I learned about magnetomotive force. It's number of turns times current, or N times I. So if I want more force, I'll just double the number of turns on my coil.
Ah, yes, the more turns equals more power fallacy.
Why is it a fallacy, though? The math says N times I. More N should mean more force.
It does if you can keep the current the exact same. But here's the catch. Copper wire has resistance. If you double the number of turns, you're doubling the physical length of the wire.
So you're doubling the resistance.
Right, and Ohm's law is stubborn. If resistance doubles and your voltage is fixed like from a power supply or battery, your current gets cut in half.
So you doubled N, but you halved I.
And you end up with the exact same magnetic force, but now your coil is twice as big and twice as expensive. It's a zero-sum game unless you change the wire gauge or bump up the voltage. You have to optimize, you can't just add more.
It's never as simple as just add more wire. Okay, last question. We see this in speakers and some fancy actuators. They put a permanent magnet inside the coil assembly. Why? Isn't the coil supposed to be the magnet?
This is a phenomenal efficiency hack. We just talked about how much heat Alex created just to hold the latch. He's essentially renting the magnetic field using electricity, and he pays for that rent in heat.
And a permanent magnet owns the field.
Exactly. A permanent magnet provides a strong bias field for free. It's there forever with zero energy cost. So in a speaker or a specialized motor, you use the permanent magnet to do the heavy lifting of creating the baseline field.
Okay.
Then you use your coil current only to modulate that field, to push or pull against the bias.
So you get way more force for way less current.
Exactly. You are using the electricity for fine control, not just for the brute force creation of the field. It's much smarter design.
So bringing it all back to Alex. He started with a plastic spool and a dream, and he ended up navigating vector calculus, energy methods, magnetic circuits, and thermal management.
And hopefully you realize that a solenoid isn't just a magnet, it's an energy conversion machine. It's a device that is constantly trying to minimize its reluctance and maximize its inductance.
And once you understand what the machine wants, to close that air gap, to store energy, you can design around it.
Yeah.
You stop fighting the physics and start using it.
Precisely.
Before we wrap up, is there one final image or concept you want to leave everyone with? Something for you listening to visualize when you're staring at a coil of wire.
Yes. We talked extensively about the energy method, but sometimes it helps to think in terms of magnetic pressure.
Magnetic pressure. Like a gas.
Sort of, yes. Imagine the magnetic field lines in that air gap aren't just abstract lines. Imagine they are rubber bands that are packed tightly together.
Okay, rubber bands.
These rubber bands have two properties. One, they want to be as short as possible. They are under tension, that is the physical force pulling the plunger and the lines trying to shorten themselves.
Got it.
But two, they push sideways against each other. They hate being crowded. This is the magnetic pressure.
So they are pulling lengthwise and pushing sideways.
Right, and that tension, that deep desire to shorten, is what snapped Alex's latch shut. He simply provided a path, the iron core, that allowed those rubber bands to relax and get short. If you can visualize the field as a bundle of tension looking for release, you can intuitively troubleshoot almost any magnetic actuator.
The rubber band theory of magnetism. I like it. It takes the invisible and makes it completely tactile.
It works surprisingly well in the field.
Well, Alex, wherever you are, I hope your door is locked tight and your coil isn't overheating.
And watch out for that suckback effect if you try to build the launcher.
Absolutely. Thanks for joining us for this deep dive into the deceptively complex world of solenoids. And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.